there, I am Anusha. I am a software engineer at Google and I work for the Google Assistant Communications team out of the Mountain View office in California in the US.
Hello, my name is Bartosz, and I have been a software developer at Google in beautiful Waterloo, Canada for almost 2 years. I currently work with the Display Ads Experiments team and the Google Kickstart team, which is organizing another coding competition run by Google.
Bartosz and I are going to talk about the problem Schrödinger and Pavlov for CodeJam 2022's World Finals.
We both have experience as contestants in coding competitions like CodeJam and Kickstart, and we are very excited to be on the other side, setting up challenges for all of you.
It is 1935, and a meeting between two Nobel Prize winners is producing extraordinary results. Schrödinger, a famous physicist, invites Pavlov, a famous physiologist, to see his experiments with cats in boxes. Pavlov brought his dog with him to keep up with his own research, and the combination proved interesting to say the least. Let's start out with what the problem is asking for. We are given n boxes in a row. Schrödinger's cats may be present in some of them. Each box is only big enough to hold a single cat. The boxes are connected by a series of one-way tunnels. Each box is the starting point of exactly one tunnel, but can be the destination of 0, 1, or multiple tunnels.
The cats can move in one direction from one box to another if a tunnel exists between them. Note here that the cat can only move if the destination box is empty, as boxes are not big enough for more than one cat. Cats are usually mellow and calm and prefer to rest inside their boxes if nothing alarms them.
Pavlov's dog walks past the boxes from 1 to n and barks at each box in turn. If a cat is present in the box, it tries to escape through the tunnel, leaving that box. Note that the cat cannot use the tunnel if the destination is already occupied by some other cat.
Let us take a look at the example. Here we have 4 boxes, and we have a cat in the first, second, and fourth box. There are tunnels from the first box to the second one, from the second box to the third one, from the third box to the first one, and from the fourth box to the third one.
Now let's consider the dog running from left to right. When the dog approaches the first box, it startles the cat inside, which tries to escape to the second box. However, as the box is already occupied, it cannot go there. Then the dog approaches the second box and startles the cat inside this box. The cat escapes through the second tunnel and ends up in the third box, which was free. Now the dog approaches the third box, which is currently occupied by the cat that escaped from the second box. The cat gets startled again, but is unable to escape as the first box is already occupied. Finally, the dog reaches the last box. The cat inside this box is startled as well and tries to escape, but is not able to, as the third box is already occupied.
The objective of this problem is to predict if the last box contains a cat when the dog finishes running past all the boxes and reaches the last one. In this example, we can see that the last box will contain a cat in the end. But that's not the whole problem. In pure Schrödinger's cat tradition, we are not certain whether some boxes contain a cat or not. If we have k unknown boxes, then we have 2 to the power of k hypothetical situations, and we want to consider for all of these situations if a cat would be left in the last box. The output of the problem should be the number of ways that would result in a cat being in the last box. You need to write a program that can give an answer to all situations up to 5,000 boxes. It is common for CodeJam problems to deal with large numbers up to thousands or millions of digits long. That is easier in some programming languages than others, so to keep things fair, we often only require giving the value modulo a large prime, such as billion plus 7.
There is also an easier version of this problem that you can solve. In this version, we have at most 100 boxes, and all the tunnels connect to nearby boxes. The farthest connected one can be 5 boxes away.
We are going to stop here to avoid any spoilers. We can't wait to see some creative approaches our finalists take to tackle this problem.
Stay tuned after the contest ends to see a full walkthrough of the solution and make sure to check out the analysis page for the solution after the round ends. Goodbye!
Hello everyone, this is Mohammed Yasri. I'm a software engineer in Surf Search team in Search Ranking. I'm also part of CodeJam coding competition team. Right now we will walk through Schrödinger and Pavlov solution. So if we are, as a quick recap for Schrödinger and Pavlov, we have a row of n boxes. These boxes contain a cat. The boxes, some boxes contain a cat, some boxes don't contain any cat, and some boxes may or may not contain a cat. So if boxes with 1 contains a cat, boxes with 0 doesn't contain a cat, boxes with question mark may or may not contain a cat. And our objective here is to compute how many configuration lead to a cat in the last box after the whole process. The process goes from left to right, from box number 1 to box number n, and at each step, if the box contains a cat right now, it can move through a tunnel to the next box, only if the next box is empty. And of course, we see that depending on the uncertain boxes, the boxes that may or may not contain a cat, it can change the number of final configurations, our solution. So for example, if we have the number of empty boxes, the uncertain boxes is k, so we have final configurations with a total of 2 to the power of k. So for test set 1, we have 2 special limits. So the first limit is the number of boxes is up to 100. And also the tunnels has a limit. So a box, let's say we have box number I, it can only go, the tunnel can only go to any box within a distance of 5. So I plus 5 or I minus 5, any box in this distance. It can't go to any box further than this distance. With all of this in mind, for test set 1 we can have a dynamic programming solution. This solution has this state. So the current box we are at right now and the state of the previous 5 boxes and also the state of the current boxes, the current box, and the state of the next 5 boxes. And why is that? Because we only move 5 steps, at most 5 steps ahead or 5 steps previous. And what the DB tries to compute is what is the number of configurations that will end up if we are at this box right now, and the previous 5 boxes were at this state, and the current state is this state, and the next 5 boxes are currently at this state. And of course, this dimension is up to 100, this dimension, and the second dimension is up to 2 power 5, and the third dimension is only 2 states. The last dimension is also 2 to the power 5. So the DB state is a total of 100 times 2 to the power of 11, or n times 2 to the power of 11. So we go simulate the process from box number 1 to box number n. If the box contains a cat, we try to move it if the next box is empty. And of course, if the next box is a maybe, so it can contain a cat or maybe it's empty, we branch the condition. We try if it's contain a cat, and if we try if it doesn't contain a cat. And also if the current box is a maybe box, then we also branch. So we try twice. We try if it does contain a cat and if it doesn't contain a cat. And doing so, at the end, we will count the number of configurations that end up with a cat at the very last box. This is fast enough to pass test set 1. With further analysis, we can get rid of the exponential factor. For the full details, you can check out the full analysis on go.co on g.co/goodlam. That's it for now. Thank you.